Lightning strikes. Giant sparks of static electricity tear through the atmosphere at 60 million miles an hour. Up to 1 billion volts rip the air apart. In that instant, the current creates light waves. We see a brilliant bolt of light race across the sky. Air inside heats up to more than 50,000 degrees Fahrenheit. It expands so rapidly, it explodes. We hear a deafening clap of thunder. It all happens in less than the blink of an eye, up to 8 million times every day. This is one of nature's most frequent, best observed phenomena. But it's also one of the least understood.
We probably know more about how a star explodes halfway across the galaxy than how lightning works just a few miles above our heads.
Yeah, Mr. White. Yes, science.
We probably know more about how a star explodes halfway across the galaxy.
But scientists don't fully understand the extreme physics of supernova explosions. But the details of how the magnetic fields form and how the particles are accelerated have been a mystery.
Thanks to circumstantial cosmic evidence collected, experts estimate that,
Yes, science.
like circumstantial evidence, astonishing discoveries of new ultra-bright supernovas like 2005 AP and others have opened up a whole new avenue of inquiry.
We probably know more about how a star explodes halfway across the galaxy.
How one of them makes gamma rays and the other makes an ordinary supernova is still one of the big mysteries. Nobody really knows how that works. Nobody really knows how that works.
But the details of how the magnetic fields form and how the particles are accelerated have been a mystery. But scientists don't fully understand the
Yes, science.
Halfway across the galaxy,
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much.
So what this means is he's been looking for all different possible mechanisms, both from laboratory physics and theoretical physics and different ideas, and he's now come up with 59 possible redshift mechanisms. But the whole issue of the Big Bang and modern cosmology is built around the notion of only one of those interpretations.
If that one crucial assumption is incorrect, then our picture falls apart.
halfway across the galaxy,
I think a good example is this NGC 4319 object, where you can actually see the luminous connection going from the center of the galaxy to the quasar Markarian 205.
Well, that means, in fact, that the redshifts are not pure Doppler effects, and they are simply not reliable as indicators of distance.
That's right.
Yes, science.
Scientists are using every technological tool in the box to see lightning as it's never been seen before. And they're discovering that it's more powerful.
You're talking about something that's up to 1 billion volts. It's 200,000 amps. It's a small nuclear power plant. It's huge.
And more important than ever imagined.
It's probably one of those fundamental parts of the equation that really contribute to life on Earth.
To unlock its secrets, we follow a lightning bolt on its journey from creation to destruction and beyond. Darwin is the perfect place to investigate one of nature's biggest mysteries. What sparks a lightning bolt? An international team of scientists are here to find out. They use radar and a fleet of aircraft to look for the answer deep inside Darwin's monster storm clouds. A potent cocktail of heat and moist tropical air means these are no ordinary clouds. Called cumulonimbus, they can rise up to 40,000 feet at speeds of 60 miles an hour. 13 miles up, twice as high as a passenger jet. Above the storm, a modified former Russian spy plane collects data about the cloud below. Somewhere inside this cloud, lightning is preparing to strike. Understanding how has puzzled scientists for centuries.
I know a bit about it and then I'll go and read up a bit more about it. This is one of those cases where you keep coming across things where people say, and we really don't know X, or we can't understand Y. It turns out even today there are significant gaps in our knowledge about how thunderstorms work.
But they think the cloud acts as a giant electrical generator. Inside the cloud, tiny water droplets rise upward. They freeze and fall back down as ice. They rub against each other. Electrically charged particles transfer from one to the other. The water and ice particles that were previously neutral are now either positively or negatively charged.
I also had no idea that charge in clouds was caused by ice smashing into each other.
And I think the other thing to emphasize is that that's the best theory. And people have done lab experiments to show that indeed you can, if you crash these little ice crystals, it's quite a hard thing to do in a lab, but if you crash little ice crystals into these bigger wet hailstones, you do create charge transfer. So we know the phenomenon does work. Whether it's really what's driving everything that's going on in thunderstorms isn't clear. And then the whole question about, well, how does the thing discharge? And there's a whole kind of phenomenology of what goes on. You can have lightning between one cloud and another, lightning within a cloud, lightning from cloud to ground. Sometimes lightning goes downwards. Sometimes it's a thing called the leader when it's going downwards. Sometimes you see the flash going back upwards with high-speed photography. So there's a very complicated lot of physics that's going on, but the underlying mechanism behind it is this charge separation, and almost certainly the underlying mechanism between that charge separation is this triboelectric effect, which causes these enormous static charges within clouds.
In terms of what triggers the lightning, like you've got these huge charges building up, is there like a critical mass or a magic number, or like what makes the lightning think, all right, enough's enough, I'm doing it?
And again, it's complicated, and it looks like the story is not that well understood. If you do the kind of the naive calculation, you find that actually there isn't enough voltage there to trigger the lightning strike.
They rub against each other.
Actually, there isn't enough voltage there to trigger the lightning strike. So then the question is, well, what is it? We see lightning strikes. And so there are some pretty extreme theories which...
The negative particles sink to the bottom of the cloud. The positive rise to the top, separating the positive and negative charges. When they reunite, lightning will strike.
Actually, there isn't enough voltage there to trigger the lightning strike.
That's the theory. That's the theory.
He talks about this and he says that the top of the thunderstorm has a positive charge and the bottom a negative one, except for a small local region of positive charge at the bottom of the cloud, which has caused everyone a lot of worry. No one seems to know why it's there, how it is important, whether it's a secondary effect of the positive rain coming down, or whether it is an essential part of the machinery. Things would be much simpler if it weren't there. So it's kind of a slightly complicated picture, but the basics are kind of fairly straightforward, which is that a lightning strike is really just an electric discharge to... Well, duh. Lightning strike is really just an electric discharge to...
People think a lightning is electricity. Well, it's effing not electricity. It is electrostatic, i.e. dielectric.
But the reality is even stranger. Air is not a good conductor. Electricity can't pass through it easily. To let the current through, the air's atomic structure must literally break apart. To do that takes millions, even billions of volts. Scientists search the skies for this huge electrical charge. But even in Darwin's massive storm clouds, it's never been found.
Yes, science!
In the story of lightning, there's a piece missing. It's a puzzle that fascinates physicist Joe Dwyer from Florida Institute of Technology.
With lightning, it's almost embarrassing. We've been studying lightning since the time of Franklin, and over 200 years, we still haven't answered the big questions. How does lightning work? How does it get started up in the thunderstorms? How does it propagate for miles through the air from way up there where it's initiated down to our feet?
One thing we can be sure of, lightning is static electricity, and you can make it at home.
Let me take my shoes off, and when I do, I'm going to rub my feet on the carpet. As I rub my feet, friction is going to separate electrical charge. Positive charge is going one way, negative charge the other. Now when charges separate, they want to get back together. A large electric field can build up, and when this happens, you can get a spark. We think that something like that is going on inside a thundercloud when it makes lightning.
To send a current across this tiny distance takes up to 25,000 volts. But lightning bolts can be up to 120 miles long. Sending a current through this much air takes millions of volts, a massive electrical charge that so far scientists have failed to find.
Yes, science!
You have to ask, well, where is the finger that's concentrating the charge to making the big fields to produce the spark? And we're having a really hard time figuring out what that finger is.
So that's when life gets really complicated. So there's a potential difference between the bottom of the cloud now, which is quite strongly negatively charged, and the ground, which actually is positively charged. So there are...
Why is the ground positively charged?
That's, again, another very good question. And it's, again, something which is sort of a slightly open question as to whether it is. If you go away from a thundercloud and ask whether, whether the ground is positive relative to the air higher up, it turns out that it is. And so something, again, is continually charging the Earth up, or removing charge from the Earth, again, and it's probably, again, some quite subtle static electricity effect.
Are you telling me that the Earth is positively charged?
It is. There's a huge voltage between the Earth and the top of your head, yeah.
Thunderstorms are violent. Lightning is unpredictable. Getting close enough to make measurements is virtually impossible. Scientists can't get to the lightning, so at the University of Florida's International Center for Lightning Research, they bring the lightning to the scientists.
What we did is that we used rocket-triggered lightning. You can tell lightning where and when to strike.
Dwyer and the team fire a rocket into a charged storm cloud.
Ready to fire. Arming rocket. 5, 4, 3, 2, 1, fire.
It trails a copper wire that acts like a lightning conductor. Millions of volts of electricity race from the cloud to the ground. Dwyer uses data from this to investigate how lightning can pass through miles of air. And he looks for the answer in outer space.
Space may be the final frontier, but it's made in a Hollywood basement.
In a galaxy far away, a star explodes.
But scientists don't fully understand the
Millions of microscopic electrically charged particles are forced out into space.
You actually need to ask a slightly deeper question, which is, what do I actually mean by a particle? So you could be forgiven. The way I've described this to you in the last few minutes, you could get the idea that maybe these particles are somehow like little Lego bricks, or they're a bit like the Victorian atoms. They're sort of solid little points that move around and stick together. But actually, that's not what modern particle physics tells us particles are. In fact, particles aren't really what matters at all. Our field is kind of badly named in a sense. What actually we think of as being fundamental are not particles, but fields. So, not particles, but fields. So, field, we've all probably, if you've ever held a magnet next to a piece of steel or iron, you felt the effect of a field. So a field is something that can cause, for example, a force to be exerted over a distance where there's no physical stuff actually causing that force to be exerted.
No physical stuff.
There was a guy called Hess who was floating around in a hot air balloon, and he noticed there was some radiation hitting him. He detected this radiation, and it's basically very, very high energy protons. They're just coming from somewhere, and they're hitting the Earth, and we really didn't know where they came from.
Henri Becquerel discovered radioactivity with uranium in 1896. Scientists sought a way to measure it. How radioactive were different materials? And one way to do this is with a gold leaf electrometer. When it's charged, the leaf is repelled, and you can measure the amount of charge by the angle of the leaf. Now, if ionizing radiation enters the chamber, it rips electrons off air molecules, creating positive and negative charges. Opposite charges are attracted to the leaf, discharging it over time. The higher the level of ionizing radiation, the faster the device discharges. In 1910, Theodore Wolff took his electrometer to the top of the Eiffel Tower. Since radioactivity was found in the soil and rocks of Earth, he expected that 300 meters up, the radiation would be just a few % of the ground radiation. Instead, he found only a slight decrease. In 1911, Austrian physicist Victor Hess decided to take this experiment further. Literally. He loaded electroscopes into the basket of a hydrogen balloon. In his first 2 flights, he observed the same thing as Wolff. Up to an altitude of 1,100 meters, both trips revealed no fundamental change in radiation compared to the values observed on the ground. But the next year, he conducted 7 balloon flights, up to an altitude of 5,200 meters. And here, he discovered something remarkable. While there was an initial drop in radiation for the first several hundred meters, above 1 kilometer or so, the level increased with increasing altitude. At his maximum height, the level of radiation was several times greater than it was on the ground. The radiation appeared to be coming not from the Earth, but from the sky. Hess scheduled one of his balloon flights during a solar eclipse, and as the moon passed in front of the sun, he carefully watched his instruments. But the readings were unaffected. Even with the sun half covered, the level of radiation was the same. Since no influence of the eclipse on the penetrating radiation was noted, we conclude that even if a part of the radiation should be of cosmic origin, it hardly emanates from the sun. Victor Hess had discovered cosmic rays, high-energy radiation from space. But what were these rays exactly, and where were they coming from?
These are cosmic rays. Traveling at nearly the speed of light, they race across millions of miles.
Light speed is too slow. Light speed too slow? Yes, we're gonna have to go right to ludicrous speed. Ludicrous speed.
Millions of light years.
Well, that means, in fact, that the redshifts are not pure Doppler effects, and they are simply not reliable as indicators of distance.
That's right.
To reach Earth.
It is photoshopped, but it's has to be.
And as you can see here, there has been some modifications.
To reach Earth.
Are you seeing this for yourselves? Are you seeing this for yourselves, ladies and gentlemen? This is supposed to be credible information.
Only the Earth is moving, and you can see the car is just sitting there stationary. So if this is not a dead-to-rights bust for CGI people, then I don't know what to tell you.
To reach Earth.
Hey, no one has even mentioned the speed of the craft or the curvature of the Earth yet. It's pretty crazy.
17,500 miles an hour they're both traveling, and the curvature of the Earth behind them.
Ah, never mind. Let's watch again. Whoa, watch out for that curve.
Dwyer wonders, could cosmic rays explain how electricity travels through miles of air? Billions of these rays bombard our planet every second. They're invisible and inaudible.
Not particles, but fields. So
it could be that a high-energy cosmic ray from space has crashed into the cloud, created a kind of a shower of charge, and that's enough to kind of create the ionization which just kicks the thing off. But what it is exactly, really, again, really isn't that well understood why it is that lightning triggers at one moment and not another moment.
That's crazy. Typical astronomer.
Well, it's all down to astronomy, really, isn't it? Yeah. Well, it's all down to astronomy, really, isn't it? Yeah. Well, it's all down to astronomy, really, isn't it? Yeah. Well, it's all down to astronomy, really, isn't it? Yeah. Well, it's all down to astronomy, really, isn't it? Yeah. Well, it's all down to astronomy, really, isn't it? Yeah.
Heard that theory? That's amazing.
You know that, yeah.
But is that one of the fringe theories?
I don't think so. That's the trouble. I've been really struggling to find, usually there's one narrative that I can use for a video like this that says most people think it's this way, right? It really is still quite complicated and messy. And although we sort of understand quite a lot of the underlying basic physics, how it all gets put together in detail and what all the elements are still isn't clear.
And Wikipedia hasn't got the answer.
Even Wikipedia doesn't have the answer.
But when a cosmic ray travels through the atmosphere,
radiation,
It momentarily rips apart the air's molecular structure. This produces X-rays.
Radiation?
We don't know of anything in the universe that's capable of making such high-energy, high-speed particles.
Not particles, but fields. So
Unsolved, a professor of physics at the University of Maryland, says, cosmic ray particles with energies as high as 10 to the 20th power electron volts have been measured on the ground. This is more energy than we have achieved in the most powerful man-made particle accelerators. But how do natural cosmic ray accelerators pump so much energy into these particles? This is one of the biggest mysteries in astrophysics.
not particles, but fields. So
just ask an astrophysicist to come up with an estimate for the highest speed a particle could ever go anywhere in space, which sounds kind of hard. And it is, which is why they come up with crazy situations like particles surfing on exploding supernovas, or black holes swinging particles around like slingshots. The highest energy a cosmic ray should ever have, knowing what we know now about the universe, is 10 to the 17 electron volts. The oh my god particle blows past that estimate with 1,000 times more energy. So that means there must be a new kind of object in the universe that we don't know about yet. So that's where we're at. We don't know what kind of object could make the oh my god particle, but we can speculate. One possibility is that they were made by a supermassive black hole. As black holes inhale everything within reach, they cause a huge mass of gas and dust to swirl around, which has been observed to generate incredibly energetic radiation. But scientists are a little doubtful on this one because they don't seem to see that cosmic rays come from the areas in space where we know supermassive black holes are. Another possibility is that there's some unknown force in the universe we don't know about yet. And then there's my favorite possibility. What if these cosmic rays are the result of alien experiments? Sounds crazy, but it's possible. I mean, creativity is the key to revolutionary ideas. The oh my god particle could be pollution from alien experiments.
Yes, science!
Listen, I know you're just as disappointed as me that there's no resolution to this mystery yet. But get on my excitement level because we have a clue! Cosmic rays slow down as they travel through space because they interact with the cosmic microwave background, which means that they have to be made by something close by. For watching, and by the way, this video was inspired by a chapter in the book by Daniel Whiteson and Jorge Cham called, fittingly, We Have No Idea.
Well, duh.
You should check it out. Happy physicsing!
It's not the end of the story, Brady. It's so we say we may, so maybe, okay, we think this is where, it looks like this is where these high energy guys are coming from. Is at the end of it, but there is another mystery, and that's that there's something called the GZK cutoff, and this basically says that there should be a maximum energy that any high energy cosmic ray could have, right? Now, it's about 50 million TeV. Now remember I said there were ones about 300 million TeV, so it's not hugely more, so one could say it's a bit blurry, but...
It's like 6 times more.
Well, yeah, but 6 times in cosmological terms isn't so bad, is it? 6 times in cosmological terms isn't so bad, is it?
Yes, science!
Electromagnetic waves of radiation, which can be measured. Could cosmic rays be the missing link in the story of a lightning bolt? It sounds like science fiction.
You could say that again.
It sounds like science fiction.
You could say that again.
Even the optimistic Dwyer thinks it's a long shot.
When we got our first triggered lightning and made our first X-ray measurements, I didn't even get around to looking at the data for a couple weeks, because I wasn't really expecting to see anything. When I sat down finally, there on the screen was an X-ray pulse right when the lightning occurred. I thought, well, what's the chance of that happening? I mean, right there at the same time. So we looked at the next stroke, and there was another pulse, even bigger. We looked at the next stroke, another pulse, and another pulse with the next stroke. Every time we looked, we saw a big burst of X-rays hitting our instrument at the exact time that lightning struck.
To Dwyer, it's a clue.
Oh, really?
In 1985, X-rays associated with lightning in thunderstorms, the F-106, and we ended up going on, so from there, we ended up going on this one here, and it was G. Parks et al. And
X-ray enhancements detected during thunderstorm and lightning activities.
Absolutely, of course. The results, so this is the abstract, the results obtained by an X-ray detector flown into thunderstorms on board a NASA F-106 jet are discussed. It is found that significant quantities of X-rays ranging in energy from 3 to more than 12 keV are produced within thunderstorm clouds, which support lightning discharge activity. It is inferred that the X-rays are the bremsstrahlung radiation emitted from energetic electrons that have been accelerated through runaway processes. Evidence is presented to support the contention. The structures responsible for the acceleration are strong double layers supported by the very high current densities attributed to lightning discharges. The X-ray detector system consists of a 5.04 centimeter diameter Na open bracket Ti maybe TL close bracket crystal coupled to a photomultiplier tube. Absolutely, of course.
Photomultiplier tube.
Absolutely. So basically, all these scientists got together in 1981 or whatever, 85, and they went into this jet, F-106 jet.
NASA
jet. NASA. Now, NASA, remember, NASA are the same people, same organisation
that sent men to the moon.
So you've got to remember this, okay?
Yeah.
So you think about credibility, yeah? What is it? Isn't there an acronym, never a straight answer?
Yeah, or not a space agency.
Absolutely, of course. But so we've really got to think about the credibility of this information.
Are you seeing this for yourselves, ladies and gentlemen? This is supposed to be credible information.
So let's see. So X-rays from static electricity. Now this guy is actually saying that you can get X-rays from static electricity. So given that the F-106 jet, what Parks found and his buddies found that lightning can generate X-rays, then this would be quite true then, wouldn't it?
Yeah, I know.
He's got it wired up to a
vacuum
tube rectifier.
Oh, did I say that word again?
What, a vacuum tube? Oh, tube rectifier.
Photomultiplier tube.
Absolutely. Yeah. And yeah, so he's got that, and he's got a sheet of aluminium there, I think, isn't it?
Could be.
And behind on the left, far left, he's got a Geiger counter.
Well, he's got a counter to detect
X-rays. To detect radiation or X-rays. So there we go. It's just reading not much at the moment. Okay, so he's going to wind up his
Wimshurst.
Yeah, there you go.
Away he goes.
Away he goes. Now we should start seeing, and we could start seeing that his Geiger counter is actually increasing. 174.
Yeah, and
wow.
He's got the red
512. Look at that.
Well, I think what you need to do is really have a look at the comment you left the guy.
Yeah, absolutely, of course. Yeah, you'll love this because this is brilliant.
Yeah,
you'll love this. This is brilliant.
Yeah,
because we had to leave a comment after this, and we wrote, why did you not try using the Wimshurst machine alone with the detector to detect any X-rays?
Yeah.
Remember, the video title was X-rays from static electricity.
Yeah.
So why did the guy not use his Wimshurst machine, spin his Wimshurst machine, and then use his Geiger counter near the spark to see if he can detect radiation, X-rays?
Yeah.
That's what I would have thought he would have done.
But he didn't, did he?
Because then that's simulating the lightning static discharge and any X-rays that would be formed.
Yeah, because lightning doesn't have a vacuum tube rectifier, does it?
Absolutely. Well, what's he got the vacuum tube rectifier there anyway for? Well, let's find out. But after all, you're meant to be demonstrating X-rays from static electricity. Is it the case no reading would be attained using the Wimshurst machine alone? Question mark.
Yeah.
In my understanding, it's the vacuum rectifier tube that produces the X-rays, not the static discharge from the Wimshurst machine. The title of the video ought to be Producing X-rays from a vacuum rectifier tube powered by a Wimshurst machine.
Yeah, because that reflects what the content of the video.
The content of the video. And the guy actually replied, side tube HD.
Yeah.
He wrote exactly right. So it is the rectifier tube that makes the X-rays.
Yes.
So when we do look at this video, in essence, this video is slightly incorrect with the title because it's not X-rays from static electricity. It's X-rays being generated by the vacuum tube rectifier using static powered by.
But it doesn't matter how the vacuum tube rectifier is powered. It's still X-rays from a vacuum tube rectifier. And this takes us back to our videos on electromagnetic spectrum when we talk about X-rays, and we find that to produce X-rays there's always a vacuum.
A vacuum. You need those particles, those electrons, that voltage to be accelerated. And that means you have to have a vacuum. So when we look at the information...
when we look at lightning...
Well, when we look at this information here, the X-rays associated with lightning in thunderstorms, we've got to ask ourselves, is this actually true? Because I don't think it is.
Because where's the vacuum up there?
Absolutely. Where is the vacuum?
In the lightning storms are only 13,000 feet.
13,000 feet high. You know, they're still in the troposphere.
There's no vacuum there.
Absolutely.
So how can X-rays be produced?
Absolutely. So
that takes me on to that photo multiplier tube.
Oh, the photo multiplier.
Does that photo multiplier tube have a vacuum inside?
The X-ray detector system consists of a 5.04 centimeter diameter crystal coupled to a photo multiplier tube, which could have a vacuum inside it, and that's going to generate X-rays. So when you're kitting your F-106 jet out with all of this electrical equipment to detect your X-rays,
it could be that very equipment.
It could well be the equipment that's generating
the X-rays.
Yeah, because for the life of us, we can't understand how a lightning static electrical discharge from the sky, from the clouds, thunderstorm, can generate X-rays.
Yeah.
Especially given this information where the guy's actually using the
vacuum tube
rectifier to generate X-rays.
Yeah, and also the fact that you always need a vacuum to generate X-rays.
Absolutely, yeah.
Crookes tube has a vacuum.
Crookes tube, absolutely, of course. So, absolutely, yeah.
I think we've done it there.
Every time we looked, we saw a big burst of X-rays hitting our instrument.
What we're going to do is play with some high voltage and see if we get X-rays emitted. Some of you might wonder, if you're playing with Tesla coils or high voltage, is there a risk of X-rays being produced when you do that? So we're going to find out. Well, this is our Geiger counter, and at the moment it's just reading a very low background count. This is in microsieverts, and obviously that's going to be our baseline, and if we can see if we get an elevation on that with some high voltage. Right, this is our first high voltage test, approximately 200,000 volts. Let's see if we get any X-rays. Mind your ear holes, by the way. Nothing detected, but my nostrils detect ozone. Let's increase the current slightly. Nothing noticeable. Tempted to put a small lamp on the circuit. Right, we've got a small lamp there. Right, we've now got a small fluorescent tube in there. Nothing exciting. On there, as you can see, we've got a tongue dart lamp. Let's see if that has any effect at all. Let's find out. See, we'll know when we've got X-rays because the alarm will go off. Stand by. No. Well, so far, guys, no X-rays produced. However, what about if we have high voltage in a vacuum tube, like this GU81 transmitter tube, capable of switching 50 megahertz? What if we put high voltage on this? Is this going to emit X-rays? I think so.
So do I.
Very slightly, isn't it?
Mm.
That isn't worth worrying about. So we'll up it a little bit more. That's still not a great deal. Oh look, that's triggered that alarm on that. So that has detected X-rays. But that's really low.
24.
That's very, very low. I wouldn't get excited about that. Let's see if we can intensify it a bit more. So that detected that. That whacked it up a bit, didn't it? Oh, that's a couple of dentist X-rays, that one.
Yeah.
Oh yeah, that's
Well, two.
You don't want to be in the room with too much of that.
No.
Yeah, let's turn it up a bit more. Do you want to leave the room? Yes, you probably wouldn't want to keep doing that. So the moral of the story is playing with high voltage generally is fine, but if you start putting high voltage in a vacuum tube or various other types of tubes, even some light bulbs can generate X-rays, especially television tubes. So my advice, if you're going to put high voltage through any sort of vacuum tube, get yourself a cheap Geiger counter.
Burst of X-rays hitting our instrument.
Another example of fabrication. Fabrication, absolutely. The people at NASA are going up in their little F-106 little jet. They've got their little vacuum tube, sticking outside of the aircraft.
Oh, I know what you mean.
And it's the electricity that's the static that's being accelerated through the vacuum tube, which is then generating the X-rays.
Something has changed the air's atomic structure, and he thinks that something could be cosmic rays.
If something doesn't make sense, like lightning emitting X-rays, when the very equipment that you're wanting to detect those X-rays can produce X-rays.
Oh, right, yeah.
If Dwyer's right, when a cosmic ray hits a cloud, it causes a huge momentary surge in electricity, enough to create a spark, but too brief to be measured.
Oh, how convenient!
The ray hurtles on toward the ground. The super-fast moving particles,
Not particles, but fields. So
collide with air molecules and rip them apart.
We don't know know of anything in the universe that's capable of making such high energy, high speed particles.
Actually, when it comes to smacking the Earth, most of them would just pass straight through because the Earth isn't dense enough.
Collide with air molecules.
Actually, when it comes to smacking the Earth, most of them would just pass straight through because the Earth isn't dense enough.
And most cosmic rays come through the atmosphere, come past us, go through the Earth, go through the core of the Earth, come out the other side, and keep going through space.
Yeah, most of them will pass straight through, that's correct, yeah.
Collide with air molecules.
Yeah, most of them will pass straight through, that's correct, yeah, they will.
It's amazing.
Yeah.
What you just said is one of the most insanely idiotic things I have ever heard. At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it. I award you no points, and may God have mercy on your soul.
For a fraction of a second, the air becomes electrically conductive and provides a path down which the current can run. Now, lightning can strike. Now, lightning can strike. Millions of volts of electricity race between the cloud and the ground. Lightning travels up as well as down. The air lights up. We see lightning strike, hear the air explode. In the following thousandths of a second, any remaining charge in the cloud surges up and down the channel. The bolt may appear to flicker. Lightning really does strike more than once. And all this happens up to 8 million times every day, 100 times a second. Lightning is one of nature's most common phenomena. And if Joe Dwyer's theories are right, it's also one of the most incredible.
If these ideas are correct, then there may be a connection between the lightning that we see and a star exploding halfway across the galaxy in 1 million years ago.
What you just said is one of the most insanely idiotic things I have ever heard.
But scientists don't fully understand.
Called, fittingly, we have no idea.
You could say that again.
We have no idea.
I don't care if people say subspace or zero space or counter space, the ether, it doesn't make any difference. But lightning is not a cloud-to-ground phenomena. It is a desaturation lateral into counter space. And if you've actually ever seen lightning up close and didn't close your eyes, because it is, of course, very frightening and loud, you'll actually see the desaturation in a counter space. You'll actually see the lightning pulse. And you can see that it is discharging into counter space. But it must have a ground. But the desaturation of the impulse current of the lightning is discharged into counter space. It's not discharging into the ground. Well, sure there is. There's fulgurites, and we've all seen lightning rods and the streak. Well, that's just true. It has to find a ground. Yes. Many times lightning doesn't hit ground. It will discharge into counter space halfway between the clouds and the ground. So where do you think it is grounding out then? Most lightning strikes do not make a connection between a cloud and ground. I assume most of you know that also. Anyway, the field phenomena of lightning is fascinating, especially, the many years I lived in Florida where there's an enormous amount of lightning phenomena. It's scary, it's frightening, it's dangerous as hell, obviously so, because it's ultra high voltage, and it will do some serious damage to you, obviously so. But this is not a vertical phenomenon. It is a lateral phenomenon and a discharge into counter space from the impulse current of the saturation that is generated from, just like rubbing a balloon on someone's hair, you actually generate the static electricity. I mean, what do you think the bumping of this cumulus phenomena that's actually creating a charge disparity?
Actually, there isn't enough voltage there to trigger the lightning strike.
In the volume between the ground and the cloud, and also too above the cloud. And then we have the Sprite phenomena. Nova actually had a great video on the Sprite phenomena that actually shoot up into outer space. It's absolutely beautiful. Very, very beautiful phenomena. They don't understand it, but it's beautiful.
Look above the clouds, and the story gets even stranger.
Look! What was there? Oh yeah! You see it? Yes!
On our journey, following a lightning bolt, we ventured beyond the frontiers of science fiction. But this is just the beginning. Seconds after lightning strikes, high above a thundercloud, a strange new phenomenon appears. July 6, 1989. Physicists from the University of Minnesota test out a new low-light camera. They plan to use it for a high-altitude rocket experiment. They point the camera east, a random choice, at some stars and what looks like a distant thunderstorm. They play the tape back. Something catches their attention. Two funnel-shaped flashes of light. They last for just a few thousandths of a second. The team estimates that the flashes are 20 miles above the clouds and an astonishing 12 miles tall. By pure chance, they've captured something new to science. From his research lab at Duke University, North Carolina, Professor Steve Kummer searches for these strange specters.
It's exciting to be part of something fundamentally new that no one else has seen before, and it's kind of a big surprise that these things have been there the whole time and nobody knew about it.
The shape of the firmament, do you see that? Whoa, 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 whoa. Hold up now. Wow. I think only certain solid things have shape, right? The shape of the firmament. Does everybody see that? You see that? What is a classified document? Classified by the United States government, talking about the shape of the firmament. I can tell them what the shape of it is. Right? But they're talking about this.
The twin pillars of lights flicker above a thunderstorm in the distance. So, what are they? Around the world,
it is photoshopped, but it's has to be.
Lightning scientists are on the hunt to find out. They don't have to look far.
And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines.
Scientists review hundreds of hours of video taken from the space shuttle.
With a really wide-angle lens, which curves horizontal lines.
Taken from the space shuttle.
They're cleared to separate.
Power.
Launch ready.
Take one step.
There they go. They're cleared to separate.
Power.
Launch ready.
Take one step.
There they go. They're cleared to separate.
Power.
Launch ready. Just to repeat, the shuttle did not go into space today. This was the very first time it flew by itself. It was launched from atop a 747 jumbo jet at about 21,000 feet, flew 33 miles, took a bit over 5 minutes and came into a safe landing here. There were no engines on board. Launch ready.
Take one step.
There they go. There were no engines on board.
Take one step.
There they go. It was a glider, acted like a glider, was flown like a glider, and was a successful glider.
Congratulations, it was a beautiful flight.
There were no engines on board.
taken from the space shuttle.
Wow, he's in space. Look at that. No, he's not.
The ER-2 high-altitude research plane. It's NASA's science variant of the U-2 spy plane. NASA's using it to keep an eye on the Earth, the oceans, and the atmosphere from as high as 70,000 feet.
With a really wide-angle lens, which curves horizontal lines.
To their amazement,
that stuff is flat.
There are dozens of these strange apparitions, just waiting to be identified. Low-light cameras are trained on the skies. High-altitude aircraft fly above storms. Soon, there are thousands of recorded sightings.
Everybody was surprised by how common they in fact were. It's just one of those cases, once you know what you're looking for, all of a sudden you see a lot of them.
The shape of the firmament, do you see that? Whoa, 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 whoa. Hold up now.
Scientists call them Sprites because of their elusive, ghostly appearance. They seem to dance above the thunderclouds in the night sky. In groups of 2 or 3, they last less than 10,000ths of a second. Researchers from the University of Alaska Fairbanks calculate they occur in the middle atmosphere, 25 to 60 miles above the Earth, and can extend up to 30 miles across. Observations suggest Sprites are related to lightning. But how?
First of all, what they are is they are vertically discharging lightning, right? Well, that doesn't make a whole lot of sense that the lightning would be discharging upwards, especially under the current theory of how lightning works, right? Because supposedly the electrostatics is generated by the cold and warm air currents that are passing each other, causing a friction, causing electrostatics, and then of course it is naturally discharged to the Earth because the Earth is at ground potential. But what some of the pilots started reporting, and this documentary is fascinating, even though it's 99% BS on how they arrived at it. But what I found interesting is what they discovered of where they're hitting and how this all comes about. Other than that, it's a complete NASA propaganda piece. But so what they have found out that they have these vertical discharges that are going up from the clouds, which makes no sense whatsoever because there will only be a current flow when there is another conductor or another terminal, if you will, another pole that is of sufficient difference of potential to allow a discharge upwards, right? So in the standard globe Earth model, it doesn't really make a whole lot of sense. But what's really interesting about this is that when these upward discharges occur, they are occurring at an altitude of about 100 kilometers, which, you know, again, if you've heard me talk about my idea of this electric Earth, the Earth is the kind of the cathode and the firmament would be the anode. You have to have a charge potential. We know by Richard Feynman that there is a static potential charge of 100 volts per meter that's been, you know, measured all the way up to something like, I don't know, 50 miles or whatever it was, right? Which gives us a static potential of 5 million volts. And they're saying, obviously, that it's even higher than that with these Sprites. So again, what's going on here? How are we having a current flow or an upward strike into allegedly empty space? And there isn't even enough at these altitudes, at 66 miles up, there isn't even enough atmosphere up there to cause any type of friction between air currents, right? It's just not there.
Kummer uses this data to measure the size of each bolt. He matches this with sightings of Sprites from other research stations. A pattern emerges. Sprites occur in the fractions of a second after lightning strikes, but only after the most powerful lightning bolts. Kummer thinks this huge release of energy causes a disturbance in the atmosphere above.
At these altitudes, at 66 miles up, there isn't even enough atmosphere up there to cause any type of friction between air currents, right? It's just not there.
This high-speed footage, the most detailed film of a Sprite ever shot, supports Kummer's theory. 45 miles up, electrical charge momentarily increases. It triggers a giant spark. Millions of electrically charged particles accelerate outward at 33 million feet per second. Sprites come in many shapes and sizes, from the so-called A-bomb sprite, up to 60 miles in diameter, to a tall, skinny one, less than a mile wide, and nicknamed the Diet Sprite. Elves. A pulse from a lightning bolt triggers a horizontal halo of light about 60 miles above the Earth that spreads out rapidly to a diameter of up to 250 miles.
Just about everybody who has gone with a new instrument or to a new region of the world to look above thunderstorms for something new, they have found something new.
And yet they flatten out at the top just like they were hitting something. Gee, I wonder what they're hitting. But they're doing that. So again, this is another one of those pieces of evidence that you really have to consider and set aside their BS explanation for it, because if you know even the most basic things about electricity, there has to be a static difference of potential or some sort of a cathode, anode, or terminals with a high enough potential difference that there will cause a current flow. Without that, forget about it. It isn't going to work.
But even they aren't prepared for this.
Oh yeah, see it? It was so beautiful.
Puerto Rico, 2001. A jet of blue light shoots from the top of a thundercloud and travels over 40 miles into the sky. Other sightings confirm this is not a sprite. It travels up, not down, from the cloud, not the middle atmosphere. It's an entirely new species called a blue jet.
When I saw the videos, I was like, huh, that's pretty spectacular. Wonder what those are. Blue jets are a mystery that nobody really knows what it takes to generate them.
Have you ever seen a gigantic jet? They are extremely rare, but tremendously powerful. Gigantic jets are a type of lightning discharge documented only this century that occur between some thunderstorms and the Earth's ionosphere high above them. Pictured above is the middle and top of one such jet caught last week by a lightning and meteor camera from Puerto Rico, USA. The jet traversed perhaps 70 kilometers in just under 1 second. Gigantic jets are much different from regular cloud-to-cloud and cloud-to-ground lightning. The bottoms of gigantic jets appear similar in appearance to another type cloud-to-above strike called blue jets, while the tops appear similar to upper atmosphere red sprites. Although the mechanism and trigger that causes gigantic jets is a topic of research, it is clear that the jets reduce charge imbalance between different parts of Earth's atmosphere. A good way to look for gigantic jets is to watch a powerful, but distant thunderstorm from a clear location.
Nobody really knows what it takes to generate them.
5 years after the first sprite was spotted, researchers from the University of Alaska Fairbanks hunt for sprites high above a monster storm. They use a sensitive low-light camera and capture the first ever color images of sprites. It's a spectacular surprise. What causes this colorful display? With each new discovery come new questions. But sprites are elusive, unpredictable, and almost impossible to observe at close range. So Earl Williams from MIT made his own. He calls it Sprite in a bottle.
Pressure now, Mike.
In a disused printing factory in Brockton, Massachusetts, Williams and his team use a plexiglass tube, an old steering wheel, and plenty of ingenuity to create their very own Sprite. They recreate conditions in the middle atmosphere, 50 miles above the Earth.
There's the good Sprite light. We start with a tube filled with air at atmospheric pressure, like the air in this room we're breathing. With vacuum pumps beneath the table, we pump the tube down to pressures corresponding to 50-mile altitude.
Hit the air near the ground with a current, and it produces a dazzling white light. But change the pressure, and the color changes too. By running an electrical current through the tube, they create a magical light show.
Now the question must be asked, how does a shape like this form on a millisecond scale and disappear just as quickly? To answer, let's begin by learning about electricity and what it looks like in different environments. For those who don't know, one of the most important figures in our world is Billy Yelverton. His leading our plasma lab has shaped nearly every aspect of our science, and while it looks like lightning at the start, in this sequence we shift from full atmosphere discharging to a vacuum pull that dropped the density in the chamber by a significant margin. And so from the lightning we all know to a more beam-like glowing plasma stream we go, to the strengthening of individual Birkeland filaments to the point where the discharge is as organized in those filaments as you're going to see it. Now, spring back to the Sprite image and let's imagine the three primary components at the Sprite level. For advanced observers, we are ignoring blue jets and elves for the moment.
Oh, how convenient!
You have the bulb on top, which would be the jellyfish body. In the middle, below that, you have the flares outward in the transition portion. They look like spikes. And then the jellyfish tentacles below as the more familiar arc discharge in the atmosphere. So turning some of those previous sequences sideways, and we remember that indeed, in the atmosphere, this is what lightning looks like. And the downward tentacle portion of the jellyfish sprite indeed is in the upper atmosphere. Interesting that at the electrode, we can see these flares outward from the excess power that is just a bit too much for the setup. Now, given that sprites tend to happen at the D region ionospheric boundary, where ions begin to dominate over neutral matter, and the density drops, we have a more vacuum-like discharge above that. When we put them together, we see the jellyfish sprite, and the explanation coming concurrent with the altitude at which they are seen. The jellyfish shape is a function of the global electric circuit upward current spiking through the atmosphere and into the ionosphere. The surge from the lightning below is too much for the electrode sheet. Some is returned, helping fuel the Schumann resonance, by the way, and looking like lightning. And that which escapes to the upper layers of the ionosphere appears like a space discharge due to the more electric environment and lack of density. And if there is return energy down, then the flares out are exactly what Billy did in the lab, too much energy for the electrode. Certainly, it would be hard for us to reproduce both of those at the same time in the lab.
Try that again.
Certainly, it would be hard for us to reproduce both of those at the same time in the lab. I needed to edit the start and end pieces together.
Try that again.
I needed to edit the start and end pieces together, but the Earth does not have that problem.
Try that again.
The Earth does not have that problem. The density and electromagnetism of the planet dictate that indeed it must look this way. The jellyfish sprite shows you where the energy changes drastically above our heads. Strange world up there. Eyes open. No fear.
Maxwell himself changed Ampere's law, which stated plainly that without matter, no electrostatic field can exist.
Yeah, and that is important. You know, Maxwell just out of nowhere, of course, Maxwell was, a glober. He was pushing this glober agenda, but Ampere was the guy that did these initial calculations on the electrostatic field in the first place. And like I said, guys, it even makes sense. If you don't have anything to apply a charge to, you're not going to have a charged field, right? Nothing there, nothing's going to get charged up. It's as simple as that. And we actually, now Zach and I have really, done our homework on this. And there are several mainstream physicists and engineers that are saying, how the hell could he do this? How could he do this with no evidence whatsoever? Where did Maxwell get the balls to just change this theory to say, well, you can charge, nothingness, put a charge on nothingness? Again, this is just their stupidity. And there are a lot of physicists that are disputing it. Go ahead.
Walter Lewin, former MIT physics professor of 4 decades. He even says Maxwell changed the equation with no experimental backing whatsoever. But because of the way our Earth is and the way the universe is, it has to be. He says that.
Yeah, it has to be, because it has to match their model, which again is complete fantasy. And other than made up evidence, they got no evidence at all. And that's really the truth, people. It really is. Let's continue.
But wait, as a glober, don't you at least have to admit that you consistently have to invoke ambiguity, or I don't know if incredulity is really the word, but you have to constantly appeal to the idea that you simply don't know yet, but it has to be that way. But if it wasn't that way, we could explain everything. Like, it's baffling. I don't even know what the top tier of their side says, right? Like, this is another perfect example. Oh, all observable phenomena can be perfectly explained. Everything we observe on the Earth, bam, perfectly explained. But if we assume there's a ball in space, then it doesn't adequately explain it. So we must change it, make up a fairy tale because it doesn't work. And no, we can't prove it, but it has to be that way, or what we assume is wrong. And we know that's not the case, because it can't be. It's just, I don't know. I'm blown away. Like, I don't see the people that come around and they say that horizontal doesn't mean flat, level means curved, and all this other, sea level isn't actually level, even though we have elevations. Like, those people, I don't even really consider those like real people, right? But like the top tier, they know what they're doing, right? Like, this person, Maxwell, knew what he was doing. Maxwell, if you've read any Maxwell, he was far from dumb. Not even close to the word dumb. He was not deluded enough to think that this was reality. Right, so it's like they're making a conscious decision to turn their head from observable phenomena that is explained, and then leap over to the philosophical ground they prefer that cannot be explained, and they actually band-aid and replace all actual evidence with it. It's wild. And so, like, for the people that don't even know their side, of course they don't understand the magnitude of this situation, right? But like, it's people like this, like, I hold Maxwell accountable. You see what I'm saying? Like,
absolutely.
That's the real problem. Yeah.
Absolutely. Yeah, because he's operating clearly with an agenda, just like Einstein was. And just like, fortunately, Newton was smart enough to say, no, don't you ascribe that bullshit to me. So let's continue on and finish this video up.
Without matter, no electrostatic field can exist. Maxwell changed it with no scientific evidence, allowing it to gather magically above our heads in free space.
The phenomena I've been looking at recently, Elves and Sprites. Elves is a massive plasma discharge shaped at a 400-kilometer halo. I mean, what could cause a plasma discharge to flatten itself to a wide halo and dissipate in like a millisecond? Maybe something solid and transparent. Here are some Sprites, which live under the 100-kilometer altitude and never go above 100 kilometers. These are also from electrical discharge.
Where Sprites are, that just seem to make some sort of halo effect when they hit it, like as if there's a barrier there. Why do radio transmissions bounce off it? Well, it's because it's a different atmosphere. It doesn't really make sense. Why does it actually look like there's something physically there?
So what else do we have to indicate that there may be a firmament? Here's another thing that I have pointed out several times. The Star Trek-like invisible shield found thousands of miles above Earth. Well, first of all, thousands of miles, they're saying 7,200 miles. Now, I don't believe that that is the case at all. I think it's much, much closer, but you also have to understand that when it comes to scaling in the universe, because of the scales that we are given in general, we seem to be off by a factor of about 10 to the 120th, right?
There is a crisis in cosmology. Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.
Okay, so, or up to that. So, but it's interesting. But they say stuff like, it's almost like these electrons are running into a glass wall in space, said Baker, the study's lead author, somewhat like the shields created by the force fields on Star Trek that were used to repel alien weapons. We are seeing an invisible shield blocking these electrons. It's an extremely puzzling phenomenon. Well, yes, I'm sure it is. Because there's something up there, again, in my opinion. But again, there is so much evidence, I think, that we're building this preponderance of evidence once again, that this is really kind of leaning towards the idea that there is a firmament. No matter.
Do you have an idea of what that firmament would be composed of? Are you saying it's like an electrical thing or actually a solid thing?
Well, I think that it's probably a solid thing, but it has a charge potential on it. And you know, I think that there's probably a few, and it also has optical characteristics as well. And I think that if the biblical account of, you know, where the sun and the moon are within the firmament, right, that's also something I believe that could be giving us our apparent position of the sun and moon. Because obviously they're very elusive, like a rainbow. You know, you go towards them and they seem to move away from you. You can't ever really track them down, right?
Right.
So I don't know, but I tend to think that yes, it is solid. Just biblical account.
The way I want to start this out, guys, is you've heard me talk about the model of the flat Earth and how I believe, you know, that we have our firmament, that we are within a charged box. That has the firmament over the top. Obviously, we're covered on the sides. We would have to be in order to have pressurized air pressure. That is the necessary antecedent for having air pressure is, you know, you have to have a container, right? Everybody knows that. So, but what I'm going to show you is how the mainstream science looks at our world and how they interpret it. And this is actually really, really interesting. But before we do that, I want you to learn about a little electronic component that's called a capacitor and what it does. And the reason that I'm focusing in on this capacitor is because this is one of the base elements into how this entire model functions. And ironically, you will hear mainstream acknowledge this 100% all the time. But then of course they come up with other stuff that completely denies it. And then they say, no, except for that's, anyway, they wind up sticking their foot in their mouth over and over and over again. But let's get a sense of what's going on in our Earth now. So if you can imagine in your mind, first thing, that if we are on a flat Earth, that you can, you know, look at it as like the dinner plate or a Frisbee, whatever. So you have basically a kind of a slightly elongated elliptical circle on the ground. And then above that, you would have, let's say, some crystalline or metal type of roof over it, right? And I believe this roof is at about 62 miles or 100 kilometers. So, and then of course down that, and within there, you're also going to have another chamber as the firmament is described, where the sun and the stars actually reside, right? So the first thing I want you to understand is how a capacitor works and what it does, and how this kind of gives us our model for what we're going to present today. So let's watch this. And this only takes a couple minutes and we are off. Oops.
A capacitor is similar to a battery in that both store electrical energy. But a capacitor is a much simpler device that can't produce new electrons. It only stores them. However, capacitors can do things a battery can't, as we'll show here. For the purposes of this animation, we'll focus on different parts of the current propagating through the wires at different times. When we close the switch, electricity immediately runs throughout the circuit. Although the convention is to think of electrical current as moving from positive to negative, electrons actually move from negative to positive, as we represent here with yellow particles. As you can see, the battery is not much good at powering this motor to lift this weight, because it discharges gradually, much more slowly than would a capacitor with the same charge. Here we'll learn why a capacitor is much better suited to such a task than a battery. Like a battery, a capacitor has two terminals, positive and negative. Inside the capacitor, the terminals connect to two metal plates separated by an insulator that keeps the plates from touching each other and allows them to hold opposite charges, maintaining an electric field. Capacitors can be useful for storing and quickly discharging electricity, so you can power, for example, an electric motor, as we'll show here. First, we need to charge a capacitor. By closing the switch, we create a circuit that includes both the capacitor and the battery. Electrons flow from the battery to the capacitor, where they are stored. Here, a yellow glow represents the increasing charge held by the plate.
Okay, and one thing I want you to notice here is you notice inside of the capacitor, there are essentially two plates, right? You have a plate here and a plate here. One is charged positive, one is charged negative. And when the surface area of these plates get charged up with electrons or protons or however you want to look at it, and I'm not advocating for any particulate matter anyway, all I'm saying is that there is a charge that is present there. This much is irrefutable, okay? Now, how that comes about, however you want to explain that, that's up to you. But we'll just try and keep it simple here. But what's happening is we have one plate that's positive, one plate that's negative. And so the battery is basically sending the supply of electrons and supply of protons, or shortage of electrons to the other, to create a charge differential between the two plates. And when that happens, when you have positive on one side and negative on the other, well, what happens? It's the same thing that happens with everything else, like a magnet. They attract each other, right? So that's why this is the base element of what we're talking about. And of course, you can already begin to imagine that where I'm going to take this next is I'm going to flip this up, where this plate here, I'm going to flip it up 90 degrees, and where this becomes the top plate or the firmament, and I'm going to flip, that'll bring this down to here, and that will make it the Earth, okay? And we call these Gaussian surfaces, but we'll get to that in just a minute. Let's continue.
For every electron gained by that negative plate, an electron is lost by the positive plate, maintaining the capacitor in equilibrium. Here, the red glow represents the positive charge held by the plate that increases with each parting electron. The capacitor continues to charge until it attains the voltage of the battery charging it. Now that the capacitor is fully charged, let's put all that stored energy to use. By connecting it to a new circuit, we can power a small motor. This electrical current powers the pulley to lift the weight until the charge dissipates. The electrons on the capacitor's negative terminal are drawn to its positive terminal. They rush along the path that leads there, straight through the motor. Let's watch this again. Even though the battery and the capacitor attempted this task with the same amount of charge, only the capacitor successfully powers the motor lifting the weight, because it discharges much more quickly. This feature makes capacitors useful for powering things that need a quick surge of energy, such as flash bulbs and cameras, and starter motors and audio amplifiers in your car.
All right, so there we have it. Basically, that's pretty simple how that works. And one of the advantages, of course, to this is, unlike the battery, which can only deliver so much current at a time, the capacitor can deliver a much faster stream of current than the battery can. And that, like you said, it makes it good for starter motors, it seemed like that. So, okay, so that's basically the function of a capacitor. Now, something else a capacitor does is it can act as kind of a buffer, right? It can act as if the source power maybe falters a little bit, it can also stabilize that by supplementing the source power with some discharge off the capacitor. So in other words, it makes it a fairly nice, stable, equal flow of electricity. Okay. Now, so
just about circuit board uses this as well. I mean,
oh God, yes.
Of all the stuff I've taken apart, I've never seen one that didn't have capacitors on it. Like you said, to steady that flow and take electricity, keep it nice and even. Yeah, you won't find one. They're used everywhere.
Yeah, you won't. Capacitors are used for coupling. They're used for filtering. They are used for so many purposes in electronics. And it's a very, very simple concept too. That's the great thing about it. It's just these two basic plates. Now, there's obviously several different kinds, but this is the capacitor in its base element. So you have to ask yourself, you know, what are these charged particles? Where do they come from? And the answer to that is they are using pre-existing matter that is already inside of the plates, because the charge in and of itself that's coming out of the battery that is charging other particulate matter is charging stuff like the molecules of gases in air, okay, or something like that. In other words, there has to be some sort of particulate matter present for these capacitors to work, right? They won't work ultimately in a high vacuum condition. Because why? Because there is no particulate matter, and then we've already covered the vacuum, you know, and how that works. If you don't have any particulates in there, and it takes a lot more and more and more and more power to get these particulates out of there. Well, if you don't have anything in there to charge in the first place, well, then you cannot have any electrostatic energy. And this is something that the mainstream kind of flops back and forth on, and we're going to cover that here in just a minute. But what's interesting about it is that idea not only destroys, once again, their model, but it also props up the flat earth model. So how does it do that? All right, so let's move on.
We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions. Molecules are clumps of matter that have a positive charge. These ions are moving slowly.
So did you get that? The positive clumps of ions or matter that take a positive charge, okay? Because the Earth is negatively charged, and the supply of the electrons, or positrons, I guess if you want to call it this, are actually coming down. The positively charged particles are coming down, and they are literally exerting a pressure downward. Okay.
You don't believe in gravity?
Well, it's not so much that, you know, like I don't believe in it, you know, it's just, I don't know, lately I get the feeling that I'm not so much being pulled down as I am being pushed.
Okay. This is a fact, and we are going to demonstrate this for you very clearly. So this is, again, this is what's happening in the mainstream world, and the mainstream science has no compunctions with this. Like I said, this is Feynman's work, his own work. The only problem is it's not possible on a globe Earth in the configuration that the globe works with space, and we're going to get to that. What it does work in, though, is in an enclosed type of area. But let's go over and you might want to ask yourself, well, where is the power coming from that is feeding this downward force of power that's coming down, right? And that's a very, very good question. Where is it coming from? And believe me, they have an answer, but boy, is it dumb. Okay, so Wiki says, atmospheric electricity is the study of electrical changes in the Earth's atmosphere or that of another planet. The movement of charge between the Earth's surface, the atmosphere, and the ionosphere is known as the global atmospheric electrical circuit. Now, first of all, guys, I got to tell you that the ionosphere is bullshit. It's complete crap. It's completely made up. And I don't believe for 1 second that it exists. And the reason I don't is because there's something already there that provides that. Okay. So let's continue on. It says atmospheric electricity is an interdisciplinary topic with a long history involving concepts from electrostatics, atmospheric physics, meteorology, and earth science. Thunderstorms act as a giant battery in the atmosphere, charging up the electrosphere to about 400,000 volts with respect to the surface. This sets up an electric field throughout the atmosphere, which decreases with increase in altitude. Now, guys, do you wonder why that field would decrease with an increase in altitude? Well, I'll tell you why. Because the air pressure, the particulate matter that is in our atmosphere is getting less and less and less. We are starting to go down, from the PSI range down below 1 PSI. And pretty soon we're going to be down into the torr range. 1 atmosphere is 760 torr. And you can go all the way down to almost, to 1 torr. And then you start going into logarithmic fractions of that, right? So there's a whole lot of deception put there just to keep us from understanding, first of all, how much, particulate matter there is up there. And other things. Anyway, okay, so basically, it decreases with altitude because we are losing air and gas particulates, right? The less you have of those, the less you can create an electrostatic field. That is a fact. You must have particulate matter to create an electrostatic field, okay? So what do they say feeds this top layer, right? This so-called ionosphere. They say atmospheric ions are created by cosmic rays and natural radioactivity.
We don't know of anything in the universe that's capable of making such high energy, high speed particles.
Not particles, but fields. So
that they have to be made by something close by.
Without matter, no electrostatic field can exist.
Moving the electric field, so a very small current flows through the atmosphere. Even away from thunderstorms near the surface of the Earth, the magnitude of the field is on the average around 100 volts per meter.
Are you saying that even one of the top guys as a globe proponent says there's an electric downward current on the Earth?
Yes. In fact, he's where I found out about it from. Was Richard Feynman. And it is absolutely there. There's no doubt about it. And like I said, I discovered it in my own way by, when I worked in microwave and satellite, I also did a lot of tower work. And when you go up a tower, 200, 300, 400 foot tower, and you accidentally, you're hanging up there 400 feet in the air. And if you accidentally come across something that is grounded, like the outer braid of a coax shield, and you touch it, that shit will knock you on your butt. Big time. You get a huge electrical shock. So the charge is absolutely real. It's absolutely up there. There's no doubt about it. And the really amazing thing about it, Austin, is that it is so perfectly linearly fashioned. These equipotential lines. Isn't it amazing that throughout all of these, what they're going to say actually does this, these huge inputs of voltage coming from, cosmic rays and cosmic X-rays and stuff like that, is, somehow balances out, and it acts exactly like a capacitor. So
That makes sense, bro. Cosmic waves, man, made a perfect capacitor. Duh, science.
yeah, it's absolutely amazing. So the way
hit exact cosmic rays the same amount at all times to keep our field so linear. And I mean, the electric field also pulses every day at the exact same time. It's like a heartbeat. They call it the Schumann resonance. So I think it's 4 p.m. UTC, it starts increasing, and at 7 p.m. it maxes out, and then by 1 a.m. it goes back to normal again. But this is every single day it does this, like a heartbeat. Now, to say that that's from all these random rays coming in from all this stuff, I'm not buying that.
No, that's right. It does. There's an absolute heartbeat to it. It's an amazing, 1900 UT. So it's 7 o'clock. And they explain it. They say because there's more land mass in the late afternoon than during other times of the day, such as 4 o'clock UT when the Pacific Ocean is in late afternoon local and the global circuit is at a minimum. So it's like, what the hell does that have to do with landmass? But if you guys watched a show we did a long time ago called Sunday Mass, well, we revealed in that really science doesn't have a really good definition for what mass actually is. And there are so many different viewpoints of it that they can't even make any sense of it themselves. Every single PhD physicist has a different take on it, which is different than Einstein's take, which, says, well, if you add motion to it, then mass becomes infinite, on and on and on. It's just it's a mess, right? It's a mess. So where do they say that we get it? Okay, so what was the source of the large-scale electric field, and why was it not quickly reduced to zero by charges in the conducting fluid? What was the source of the conducting fluid? Or, in other words, why didn't the large-scale electric field sweep away all the free charge in the atmosphere? Another critical discovery came in 1911 when Victor Hess was conducting atmospheric electricity experiments to study radioactive ions in the air. Using a balloon experiment, he found that the conductivity increased with altitude rather than the expected decrease. Now, this is a mainstream document, so geez, isn't that amazing that they would say that, okay? Thus leading to the discovery of cosmic radiation. And they're saying that these cosmic radiations, is it this one? Actually come up to like 1 giga electron volt, this huge amount of electrical power that's coming in, which clearly is not coming in. And even if it was, it would be blocked. How do I know that? Well, I know that because of this. You guys have to remember this because I've used this so many times. The invisible shield found thousands of miles above Earth blocks killer electrons. So, we had this brought out by Colorado State University or University of Colorado at Boulder. And it was verified by Massachusetts Institute of Technology and a host of other people. When basically, they came out and said, wow, this is so weird, but there's something up there at 7,200 miles and it's blocking all these electrons that are coming in, these killer electrons, this source for the field that they're telling us is providing this perfectly stable 100 volt per meter Gaussian type of surface. Well, sorry, Charlie. This isn't the only time that they contradict themselves either, by the way. When you read several of these articles, at some points they will say that it's there, other points they won't. Of course, why do I say that the top layer or the bottom layer of the firmament is actually at about 62 miles? Well, because so many things happen at 62 miles. One of the things is the alleged sodium layer, right, of the laser guide star, where they can, apparently shine a laser onto the sodium layer of the atmosphere, and it will fluoresce an artificial star with low magnitude or high brightness so that they can then correct the distortion that's created by the atmosphere, right? We also have Sprites and Elves, right? Which discharge in an upward direction. And again, in order to have a discharge from one area to another, in other words, when they see these discharges from a cloud, well, we know where one of the area the discharge is coming from, and clouds will definitely accumulate a charge because of friction in the atmosphere, et cetera, et cetera, et cetera. But the odd thing about it is they discharge up, and when they do discharge up, they all flatten out perfectly right at about 62 miles, right? So I'm convinced that there's something there at 62 miles. What is it that I think is there? I think that it is the top Gaussian plate of the firmament. So let's listen to this guy and talk about equipotential surfaces and what he says about Gaussian plates. And then we're going to cover some more of this stuff because I really need to get this through to you guys. This is so obvious. This is what mainstream science tells us we already have, but their explanation for it is ridiculous, and our explanation for it makes perfect sense. Why in the world at 62 miles where, you know, I don't even know what the what the torr is. It's probably 10 to the negative sixth, something like that at that altitude. Why would there be a layer of sodium there that's light enough to be able to fluorescent? That makes no sense. Where is this particulate matter coming from, and why is it sitting there? They have no answers for that. They're just making stuff up. You know, point blank. So, all right, so let's listen to this guy and what he says about this, and then we're going to talk a little bit more about Gaussian surfaces.
So these lines that I drew here, now of course these lines really represent surfaces because these are plates that are parallel to each other. So these are like regions or planes or surfaces. So all along that surface the potential is 80 volts. All along the next surface it's 60 volts and so forth. So these are what we call equipotential surfaces because there the potential is the same, equal, and so we call them their equipotential surfaces.
Okay, actually they're Gaussian surfaces, but whatever. What they produce is an equipotential, perfectly linear, predictable voltage at a specific point in space. Well, you got to ask yourself, how is it that we can make these predictions and then verify those predictions with our measurements, like 100 volts per meter? And it doesn't vary from that very much, guys. The biggest variation is 1900 UTC, where there's the biggest variation from that, and that's all in Richard Feynman's paper. But you have to ask yourself, how is it that they're able to get that 100 volts per meter and standardize it if something isn't providing a continuous feed at the exact same voltage virtually all the time on the top side of the feed? Because the Earth sure as heck isn't changing, you know, its potential or anything like that. Earth is ground. Earth is where the electric voltages return to. So again, you have to have something that is providing the electrical charge, the charged particulates, the charged matter itself, in order to be able to even predict this at all. And yet they do. So let's listen to a couple more minutes of this and then I'm going to switch over to another one.
Now what's interesting about them is if you travel along an equipotential surface, if you travel along that surface, the potential doesn't change at all. But in other words, if you take a charge and you move it along an equipotential surface, there's no work involved because the potential doesn't change. That means you're traveling perpendicular to the electric field. So it's
right. And the same goes for when you travel along these equipotential lines. If you take a hot air balloon up to 1,000 feet, right, and you basically get, you know, a voltage there, and you take a voltage measurement there, and then you just migrate sideways, you know, to left, right, forward, backward, whatever, that voltage is not going to change. It's going to remain the same as long as you don't change a vertical elevation. Now, there will be some small variances, but nothing, you know, nothing of any, you know, great concern, right? So again, it's like, wow, for something that just exploded, you know, from nothing into everything, this seems like an incredibly constructed type of electrical field. Why would that be there? What could it possibly do? Why is it there? Well, we're going to get to that. Let's continue.
It's really important to notice here that equipotential surfaces are always perpendicular to the electric field, and therefore traveling along equipotential surfaces means traveling perpendicular to the electric field, means it requires no work if a charge is moved along an equipotential surface. All right, so hopefully that gives you a feel of what equipotential surfaces are. Potential doesn't change. Work is not required to move from point A to point B. Let's do a quick example. Let's say that...
Okay.
Yeah, what he means by work is not required, it means that the force of the electric potential, it'll move along with that force. So if you put something like right underneath that first red line where that E is, it will move to the right and it'll do it all by itself without any other force applied to it. Now, if you wanted to go from the right to the left, you would have to add force to go against that electric field. It's like lifting something up in the air. You have to do it with force, but when you drop it, you just let it go and it follows those equipotential lines down to the negative surface.
And again, the explanation in the flat Earth model is so much more simple, and there is so much evidence for it. It's just like, you know, the Globers. Oh yeah, show us evidence of your firmament. How many shows have I done? You know, showing not only the NASA, U.S. Army, CIA documentation talking about the firmament, but all the weird things that happen at 62 miles. The sodium layer, the ionosphere area that's supposedly bouncing around up there, Sprites, Elves. There is something absolutely positively there. And the fact that every time we watch a launch, they all arc off before they get anywhere near 62 miles. So, and by the way, the math equations doing this are virtually identical to the equations that calculate gravity. Gee, that's just, you know, coincidence, right?
Yeah, the equation is exactly the same.
Yes, it is.
I mean, there's no real difference at all.
Yep.
Yeah, it's crazy.
But people buy it, you know, we're just going to swallow it up because that's what NASA tells us.
We want to describe complex situations involving charged particles using more than just Coulomb's law. If we have an object with a known amount of net charge, can we predict how other electric charges will react when they pass nearby? Well, British scientist Michael Faraday came up with a way to do just that. He hypothesized that every charged object generates an electric field that permeates space and exerts a force on all charged particles it encounters.
Okay, so what she just said is he hypothesized that every charged object generates an electric field that permeates space and exerts a force on all charged particles it encounters. Now again, guys, when you go up into this alleged outer space where you have vacuums of 10 to the negative 17 torr, where it takes the power is unimaginable. In fact, we can't even get to half. You know, we can't generate, with all of our best equipment here on Earth, we can't even generate half of what it takes to get to that level of vacuum in outer space. In other words, there's nothing up there to charge. There are no particles to charge. It is essentially void. Yeah, 10 to the negative 17 particles. It's got some particles in it, but in comparison to the rest of mass, there's nothing there to charge, and especially nothing that is going to handle the 100 giga electron volts that they say are feeding the incoming cosmic rays for this equipotential force that makes it down to the ground at 100 volts per meter. Just doesn't happen, guys. So first of all, we got Faraday saying that, and you can take that to the bank. But with that caveat, on all charged particles it encounters. No particles, no charge, folks. Basically, to sum it up, guys, we have a couple different things that we've learned today, right? That we have this equipotential static field that goes up in a very nearly perfectly linear form from 0 volts on the ground to 100 volts at 1 meter up, 200 volts at 2 meters up, 300 volts at 3 meters up. Feynman says it's been measured all the way to 50 kilometers, which is 31 miles. And I'm saying that the firmament is exactly double that. The bottom layer of the firmament is exactly double that at 62 miles. And that basically gives us a 10 million volt electrostatic field potential between the firmament and the earth. Now, these voltages can become additive and subtractive, and they can build up to much larger charges, depending on things that are going on in the atmosphere. But the bottom line is that underlying this is always that voltage. It's the voltage that everything runs on.
It's never been recreated ever, like the ionosphere. In a vacuum, getting one charge to travel from one object to another in a vacuum has never been done. And I've only found 3 papers where physicists have brought this up, and this goes back over 100 years now. And there's only been 3 physicists that write, hey, why is Maxwell's equation, first equation and fourth equation contradict each other?
Yeah.
So how many of these physicists actually know what they're talking about and actually comprehend what these equations really mean and don't just memorize and regurgitate them?
Yeah,
It's
exactly.
scary when you think of.
Again, this is where, when you're NASA and you're science and you use that word science, science says that, this is the mass of this, and therefore it's going to have this manner of attraction, gravitational, blah, 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 blah. They can get away with that stuff because nobody can test it. Now, the beautiful thing about what Zach and I are proposing here is that we can test it. We have tested it. And we can prove, even by reversing the gravitational effect by reversing the field itself. What more do you want? I mean, come on. What's the better theory? One that you can't prove anything, or one that we have every single element that is at question that we can vary? There it is.
It is a steady, gradual rise in potential, which tells us, according to the laws of electricity, that we are between 2 Gaussian surfaces.
Yeah, exactly. It tells us that we're pretty much in between something that is artificially created or divinely created, however you want to look at it. Regardless, it is technology, and it is very simple technology. It is an electrostatic field generated by 2 Gaussian surfaces, and everything else has fallen into place. They've given us everything we need to then work out what gravity is, to work out how spiders fly, to work out all kinds of things. Isn't it amazing?
Now we're closer than ever to unlocking its secrets.
Gas dome. Earth is not a closed system.
Gas dome.
The Earth is a closed system.
Glass dome. Get it? Glass dome, gas dome. Are you with me?
The shape of the firmament. Do you see that? Whoa, 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 whoa. Hold up now.
Lightning storms are pretty cool, aren't they? They light up the sky, and you can't help but feel a special, exciting energy in the air. But these lightning storms usually end, and you go about living your life. But in western Venezuela, over the mouth of the Catatumbo River, there's a lightning storm that seems to be running on Energizer batteries. It just keeps going and going. Once the clock strikes 7 p.m., the lightning storm begins and doesn't relent for another 10 long hours. This happens most nights during the year. To add to the strangeness of these ongoing storms, one night in 2010 saw the storm suddenly stop in the middle of the night and not return for 6 weeks.
Imagine living in a place where you're surrounded by the sharp smell of ozone and hot, dry air. And around 300 nights per year, the sky is lit up by nearly 10 hours of continuous lightning strikes that can be seen from hundreds of kilometers away. In fact, during peak thunderstorm season, an average of 28 lightning strikes per minute hit the surface of Venezuela's Lake Maracaibo. This lake and its weird lightning have been a scientific mystery for decades. Scientists have been baffled by the fact that Catatumbo lightning happens in the same place night after night with an estimated 1.2 million strikes per year. One Venezuelan scientist who surveyed the area in the 1960s took a guess that uranium deposits in the nearby bedrock might act like a lightning magnet, drawing a disproportionate number of ground strikes, but that idea was a dead end. Another researcher thought that all this lightning was thanks to an excess of methane oozing up from nearby oil fields and swamps. Specifically, he thought that methane's molecular geometry increased the separation of positive and negative charges inside the storm clouds, which is an important step in making lightning. But neither of these hypotheses have been thoroughly supported by other scientists, so they fall short to a simpler explanation. Nowadays, researchers mostly attribute Catatumbo lightning to the area's unique topography,
and methane from a nearby oil field. Nobody actually knows for sure, though, why it happens. Everything about it is mysterious, including one moment in 2010 when it inexplicably stopped. One day, the storm just died down without explanation and seemed for a while to be over. Then, after 6 weeks of silence, it sparked up again and has been raging ever since.
Actually, there isn't enough voltage there to trigger the lightning strike.
That stuff is flat.
Well, duh.